Okay, so as you noticed perhaps in the schedule, I have something written about the alkynes. And so I wanted to give you a little bit of information because it's, maybe tempting to think, well, goodness, we're dealing with a particle in a box. And, the particle in a box. Can I get you to drop the screen here, please? Thank you. So the particle in a box system is a very simple system. It's just a single line, and we put an electron on a 7-angstrom wire or what have you. The solutions are very easy to solve. It's a sine function. The Schrodinger equation takes 4 lines. It's not a problem. The intensity is a little more difficult. I think if you count every step like I did algebraically, it maybe take 4 pages of calculus. At 12-point type. So, but still, it's pretty easy to solve. But is it relevant? I guess that's the question, right? We spend all this time looking at such a simple system. What's my point? Because a particle in a box system really isn't exactly what you're going to see in nature. You're going to see things that they don't have a potential equal to 0. They're going to have a potential with electrons and nuclei. That's not a 0 potential. You're going to have more than one dimension. So is it relevant is the question. And so I wanted to show you some examples of the alkynes where, that's a linear molecule. It's pretty close to a particle in a box. It's not exactly. We have a potential in there with nuclei and electrons and so on. But I just wanted to show you, if you have an intuition, this is my goal. If you have an intuition for how a one-dimensional system behaves, then you will just understand 3-dimensional systems. Okay? Because no one's going to get in and mathematically solve for these things by hand. We have software that does it. And these pictures come from Gaussian. But I don't want you to treat Gaussian as what we call a black box, right? You put in a question and out comes an answer and you have no idea what's in the box, right? And so I want you to have an intuition about the behavior of quantum systems. And so I went ahead and did some calculations last night on the alkynes. Now, we'll go into depth about Gaussian later. We'll actually pull the laptops out and we'll actually do some calculations in class and analyze the results. But for this point, we'll just say Gaussian's our black box. It's actually a black box. We put our molecules in and out comes a geometry. So we optimize the geometry. You can see here this optimization of the geometry first so that it minimizes the energy of the molecule and makes sure the bond links and the electron cloud and everything are at their lowest energy state. And then we went ahead, we also did a frequency calculation just because if you're going to calculate a molecule, go ahead and do the frequency calculation. It tells you the infrared and the Raman spectra and so on. So those typically go together. But we used a very minimal basis set. This Slater type orbitals with 3 Gaussians. This is the basis set, which is the smallest basis set that we can use. But the reason I did that is because I wanted the least complicated. Yes? Is it recorded? I think so. Let me check. Yeah, it's recording. Yeah, thank you. And so this STO3G basis set is the one that you're familiar with in terms of 1s, 2s, 2p, 3s, 3p, 3d, and so on. And it follows this scheme that you already have in your head. You can go to bigger basis sets, but then it starts adding d orbitals to carbon and p orbitals to hydrogen. Now that sounds ridiculous, doesn't it? Why would you put a p orbital on hydrogen? Well, do you want hydrogen to hydrogen bond? Do you want 2 water molecules to be able to hydrogen bond to each other? Then there probably needs to be some directionality to hydrogen bonding. And so in reality, the electron doesn't put itself into these little boxes of a 1s only or a 2s only or a 2p only. if a hydrogen's hydrogen bonding, then it can mix in 10% of a 2p orbital to lower the energy, because the electron has the freedom to go wherever the charges take it. It's us that are using these formulas, these functions, and putting them on the electron. This is the math that we're using to match the spectra, but the electron doesn't, it's not confined by the wave function that we put on it. Okay. Now, we've been very successful in applying these functions to atoms, ions, and molecules. But for the minimal basis set, the STO3G, I'm just using the minimal one because it matches the things that we're used to, p orbitals and s orbitals. S orbitals on a hydrogen only, no p orbitals on hydrogen, you know, and p orbitals on carbon, probably not any d orbitals because those are too high in energy for it to mix in for carbon, and so on. And then HF, this Hartree-Fock theory, governs which Hamiltonian we use. And there's lots of options in Gaussian for using a different Hamiltonian. And again, you can get a more accurate result. So we have the freedom given to electrons. If we give it more freedom, then we get a more accurate result. If we give it a higher, more complicated Hamiltonian, we get more accurate energies, we get a more accurate result. Okay. So I just went with the simplest minimal system. And these are the molecules. I did acetylene, I guess, diacetylene and triacetylene. I don't know how you would name these, but that's a good pass at it. Okay, and so here's the energy level. Well, we're focusing on this right here, right? We're focusing on two things: the second derivative operator. Remember what that's called. So what's the second derivative giving you?
Curvature.
Curvature. How curvy the wave function is. And notice it's proportional to energy. So here's the second derivative operator, and it's proportional to energy. It's going to pull these constants out, and these constants are the energies. So the higher the curvature, the higher the energy. Okay, so this is just the concept that we want to think about. And then also quantum number. So the energy is proportional to quantum number. So as quantum number goes up, energy goes up. And as, I'll say, second derivative goes up, energy goes up. So we're going to be looking at these wave functions and seeing if we can see these principles. This is the definition, or this was done for the particle in a box, not for acetylene. So what's on the screen right now is for a single electron confined to the x-axis. Okay, and let's see if we can see these same principles in a three-dimensional system. So do you see where we're going? Okay, we have the particle in a box, a one-dimensional. Oh, I said I was going to give you the handouts. That's right. I saw y'all searching around through your papers, and so this is what we're going to be looking at next. These pretty pictures. Okay. So this is the energy level diagram for a particle in a box. We see the energies are not equally spaced. We see they increase with n squared. So, 1 to 2 is a small spacing, but then, so that's essentially 1 squared to 2 squared, so 1 to 4. And then 3 squared is at 9, so 1 to 9. And then it would be 16 and 25 and so on. So that's what the energy levels would look like for a particle in a box. Here it is for these alkynes. Across the bottom we have C2H2, C4H2, and C6H2. Notice how the energy level spacings don't seem to follow any pattern because we have a more complicated system. It's not like the particle in a box where you have n squared spacings in the energy levels. Okay. But let's look to see what we can. We do have, though, higher quantum states have higher energies. Okay, so that's still the same kind of idea. If I've got an excited state, the energy is going up naturally, right? And so we would label these quantum levels from n equals 1 down at the bottom all the way up. So this one I just labeled, the ground state. If we were just to call that 1, 2, 3, 4, 5, 6. Now remember our ground state particle in a box wave function just had one lobe, right, and no nodes. And look at the ground state wave function for this acetylene molecule. No nodes. One lobe, no nodes. Okay. Now for the particle in a box, state number 2, it had 2 lobes and 1 node. 3 had 3 lobes and 2 nodes. 4 looks like this, up, down, up, down. So it had 4 lobes and 3 nodes. This is getting a little more difficult to do. 1, 2, 3, 4, 5. Okay. And then 6. 1, 2, 3, 4, 5, 6. Oops. The line was bad. It's so hard to draw, look up here and draw down here. Yeah, it is what it is. Okay. Now, we have a one-dimensional system here, so we very easily can see like the positive piece, right? Positive and negative deflection. So like in the wave, you have a positive deflection and a negative deflection. But in 3 dimensions, how do we plot that deflection intensity? We use color. And so look up here, we have, say, I'm just going to say red is positive, green is negative, positive, negative, positive, negative. And look at the 6th quantum state has 6 nodes and 5 nodes and 6 lobes. Yeah, so it's very similar to our particle in a box system. Now, one thing I'm missing a couple of energy levels on here, and those are the HOMO and the LUMO, which are the pi bonds. Since that's really not, where you had the carbon here and the carbon here, and you had the above and below, where one is shaded and one is not. So those are missing on here. I'm just talking about the sigma framework, all of the s orbitals and the pz orbitals interacting with each other. Okay. And you can see up here, later on, we'll talk about, maybe a little bit about MO theory, but when you covered MO theory, you had the 1s electron on this hydrogen, and then this is carbon. Let's call that carbon 1. So that'd be minus 2pz on carbon 1. And then it's in opposite, or actually it's in the same phase here with this carbon 2. So minus, say, a 2pz2, and then this is the opposite sign of that one, so we'll say minus 1s on atom 2 or hydrogen 2. Okay, so you could write out the atomic orbitals that make up that particular molecular orbital. Okay, so let's now extend our box. And what happens if you extend the box in the particle in a box? L is in the denominator. So we would say, yes, extending the system is going to drop the energy spacing. Do we see that in the real system? Yes. Look how our energy spacing crushes down. So these first 5 levels are now down here. So they've really crushed down in energy. So once again, extending the box gives the wave functions much less curvature because they're going over a longer space. And so their energy drops. And we can really see that by tracking this n equals 6 level. So this is the 6th level for this molecule, and this is the 6th level for this molecule. And look how cramped our 6 lobes are. And then we come over here, see how nice and spaced out they are. Same number of lobes, but less curvature. And so that curvature term, the second derivative, went down, and therefore the energy went down. And then it went down even further in this larger molecule. You see how wide these lobes are. And so because they're wide, they curve less. So the curvature is how sharp it turns, right? This sharp turn here. It's much more gradual there. and much more gradual here. And so that's causing the energy to drop. Yeah. So what I'm hoping is that you'll see this kind of analogy where, you know, this curvature in this wave function is sharper than this one over that dimension. And so that means that this bottom one is going to be lower in energy than the top one. And you can see that in the molecular orbitals. Now we get to really complicated orbitals. You can count up the number of nodes, or you can look at how many times it changes color and so on, and you can see that that's going to be really high energy. What can I do to clarify this, if you have any things that you're confused on? We'll learn how to do these calculations later. Okay. And we'll learn about the spectroscopy of these. Like, you know, if I have electrons in this level here, can they go to this level here? We'll learn how to determine if that's the case. Okay. But for today, we're going to go over to the transition dipole moment notes, and we'll look at the intensity equation. Okay. So. Okay. So we need, for light to interact with matter, there's some conditions that we have to satisfy. First of all, most of the time the matter must be charged or magnetic. You have magnetic susceptibility, which is really small, so most of the time it's the electric effect. It's the electric field of light that's interacting with charged particle or with the change in charge on a molecule, like for a vibrational motion. If there's any change to the electrical properties of the particle, then light can interact with it. And so we need interaction with this electric field. We need unequal populations of energy levels. So, you know, we need more particles down here than up here so that we can tell if something has happened. It's not that something won't happen if they're equal. It's just we won't be able to tell. Our signal goes up if we have unequal populations. And that is why we have to have stronger and stronger magnets for NMR to get more and more sensitive signal. Because there's no difference in nuclear spin. Light can't interact with that. But you put it in a magnetic field, and now you have a population difference. And so you're splitting the energy levels of that nuclear spin by putting them in a magnetic field. But if it's not a very strong magnetic field, the splitting is small. And so you have a tiny little splitting, and at room temperature, it's like 51 to 49. Okay, in terms of population difference. And so that means out of 100 molecules, you really only have a chance of moving 2 of them and seeing that. So you're only getting a 2% of the signal that you could get. You put it in like a 4 or 5 Tesla magnetic field, and now you're getting maybe 60-40 or 70-30. And then you now have 30% chance or 40% chance of getting, well, you'd have 40 over 2, you'd have 20 times more signal than you would have in the other sample. So that's why we drive to these stronger and stronger magnets, because we're trying to get this population difference in our energy levels. So a little trivial fact there. And that's governed by the Boltzmann distribution. So you could calculate that spin splitting for a proton in a particular magnetic field, and you could calculate the Boltzmann distribution between those two. What is the probability of being in the ground or excited state at given temperature? You can cool it down and drive that. And so a lot of the probes are cryogenic. You can cool things down in the NMR and get more signal. And then you have to have a significant probability for the transition, and that's what we're talking about today. This is that transition dipole moment integral. So are all of these transitions possible? We have this energy level diagram for the particle in a box. We have charged particles. We have an unequal population. But what is the probability of each of these arrows? So that's what that transition dipole moment integral will tell us. So we have transition probability is intensity. The intensity is proportional to 3 things: the Boltzmann distribution factor, the transition dipole moment integral and the Gaussian. Yeah, and we're going to just set the Gaussian aside for now because that's mostly an instrumental effect. There is a natural line width, but in general, most of our instruments are what limit our spectral resolution. And so we're just going to set the Gaussian piece aside and look at B and I. So the G is the line shape of the function. The number of molecules in the lower state is determined using that that Boltzmann distribution. So that's the unequal population piece. That's this blue piece right here. So B right there. And then the transition dipole moment integral is that probability piece. Now, when you say probability, it's a probability that these wavelengths will interact if light comes in and perturbs the ground state. So let's talk about light. We're using this X in the middle to represent light. And so this is light coming in to our system, our one-dimensional system, with this electric vector that oscillates between plus and minus. So this electric vector is positive for a while, and then it flips over to negative for a while, and it oscillates back and forth. And so it has a positive region and it has a negative region, just like our x-axis. And so it has the same symmetry as our x-axis. So we can just use the x-axis as our dipole. And that's called the dipole approximation. So this is all based upon this idea of using the x-axis as our dipole. And what we do is we multiply it by the ground state wave function or the lower state wave function, and it perturbs the wave function. And you can think of this, if I take this wave function here, so that's n equals 1, and I multiply it by x, so this is f of x equals x. And so I take this, and we'll do this sort of vector multiplication, so times, like this times that equals, it goes negative here because it's multiplied by negative numbers and positive there. So you see I have a negative number here, a positive number here, and this is all positive. So on the left half of this, it becomes negative. And on the right half of this, it remains positive. So you see what light has done? It has perturbed the ground state wave function and made it look like, if this is n prime equals 1, it made it look like this. It's just out of phase with that, but it still has the same shape. And so now this perturbed wave function is very similar to the first excited state function. And if you multiply those together, then you'll have a strong, what we call, overlap between those. And if the energy of the photon matches the energy difference, then you get a jump. So let's just, we're using that light as a oscillating electric field, and we put that electric vector along the x-axis. And so here's our transition dipole moment integral. I posted the general results here. So I'm going from n to n plus some delta n. And so delta n could be anything. It could be the full set of plus or minus 1, plus or minus 2, plus or minus 3, etc. at this point. Okay? And so we're looking at all of those possible arrows. It can jump by 1 or 2 or 3 energy levels. Okay, after 4 pages of calculus and algebra, which you've got posted, you can follow through those steps, and then you can see here's the result that comes out. Okay, so it's not too bad. I say for 4 pages only because I didn't skip any steps. Okay, so I mean, like pulling a constant out of an integral, that's a new line. Okay, so you should be able to follow it very easily, just kind of walk through. And it takes too long to do, so don't worry, I'm not going to have you do this on like an exam where you're actually writing out 4 pages of calculus. No, what I'm going to ask you on the exam is what we're doing right now. Right? This is the result. Tell me which delta n's are allowed or not. So it's the reasoning I'm after. So you're looking at this result. We see we have a difference in cosines. Okay, and so when is, what we need to evaluate this. And so let's look at our cosine function. This is cosine. We'll just call it theta. Okay. Notice whenever there's even multiples of pi, then it's +1. And when it's odd multiples of pi, it's -1. So we have this even odd thing going on in cosines. Most of the time when you end up with sines in your integrals, as a result, everything's 0 because it's a multiple of pi, and integer multiples of pi for sine functions are 0. But for cosines, we start to get an even odd dependency. And so when this piece right here, we see the delta n right there, when these are even, then we have even multiples of pi. That means this cosine piece evaluates to +1. Okay? And this is cosine 0, so that evaluates to +1. And we have a difference here, so that's equal to 0. You see that? Yeah. Okay, and so because that equals 0, then this first term of our transition dipole moment is 0. And then over here, we've got a +1, and we have a difference. And then when n is even, okay, this is really interesting. From the math, we started with just a single n here. But in doing the calculus, we ended up with a 2n. And so that makes no matter what state we start in, whether it's an even state or an odd state, it's multiplied by 2, which means they're all even, right? These are right here, all even numbers. All right? 2 times 3 is 6. That's an even number. Okay, and then delta n's. If delta n's are even, then we have the sum of 2 even numbers. That's also going to be an even number. Okay? 2 plus 4, 2 plus 6, those are all giving even numbers. And so if delta n is even, then we have even multiples of pi, so this results in a +1. Okay, so 1 minus 1 is equal to 0. So in both cases, when delta n is even, our integral result is equal to 0. Okay, now when delta n is odd, we have an odd multiple of pi here. And so then that evaluates to -1. And this is the difference. This is always +1, but it has a negative here in front of it. So -1 minus another 1 is equal to -2. Yeah, so it doesn't go to 0, it goes to -2. And then this one over here, we have a +1 for cosine 0. And then here we have, when delta n is odd, we have even numbers, but an even number plus an odd number is going to give you an odd number, like 6 plus 3, okay, will give you 9. And so then we have, so that will evaluate to -1. And so we have +1 minus a -1, which is equal to +2. Yeah, +2. And so, again, but it's non-zero. And so then we can simplify all of these results, and we have this conditional solution. So our transition dipole moment integral squared is proportional to our intensity. That tells us our relative intensities of all of our peaks. And it's equal to 0 when delta n is even. And then I did some simplification. I pulled those 2 L's, because both of these evaluated to 2. I pulled the 2 L's out front in the pi, and I left some n's and n squareds inside this piece here. So we have our physical constants here, and we have our quantum numbers and changing quantum numbers here, and it's squared when delta n equals odd. But this is nice because now we know the intensity, okay? And so we can go back to this question, and we also know our selection rules. So the selection rules are the non-zero So we call them selection rules. We're selecting which quantum changes provide peaks. So the non-zero probabilities. Okay. So it's just the odd ones. So now we know that our quantum states can jump by 1 or by 3 or by 5, but they can't jump by 2 or 4. So here's back to our results. We have these interesting results. So those jumps of 2. So 1 to 3 is 0. 2 to 4 is 0, because those are even jumps. They're jumping 2 levels. It's not allowed. Also, because the delta n's are squared, whether we're going delta n is plus 1 or delta n is minus 1, because the plus and minus, it's squared. And so we have the same probabilities for emission and absorption. That's pretty cool too. That was confirmed by Einstein. He actually solved for light absorbing, particles, and the Einstein coefficients for spontaneous absorption and spontaneous emission are equal to each other. Yeah, and so this is a result that Einstein got as well. So we're happy that the particle in a box model matches what Einstein got. It'd be problematic if he didn't. Okay, and then also skipping levels. Look at the probability of going up by 3 compared to going up by 1. So going up by 1, this is close to 1,300 in its probability. Going 1 to 2 is 1,300. Going 1 to 4 is 8. Okay. Why is that? Well, look up here. We're both starting in 1, n equals 1, but the delta n is 1 for the fundamental, but then for the first overtone is 3 here and 3 here. And so those dramatically drop the intensity, and they're squared. Okay. Okay. So this simplifies our spectra. Selection rules, it eliminates half of the possibilities. So all of those even quantum number changes are 0. So our spectrum becomes very simple. And in fact, the more symmetric the molecule, and this is a general principle, so you can write this down. The more symmetric the molecule or the system, the more restrictive the selection rules. The more symmetric the molecule or atom, the more restrictive the selection rules. I'll say it again. The more symmetric the system, whether it's a molecule or ion or what have you, the more restrictive the selection rules. We'll see this when we compare benzene to chlorobenzene. Benzene's a D6H molecule, and chlorobenzene is C2V. And that's much less symmetric than D6H. And we'll see the infrared spectrum go from benzene, say with 5 peaks, to chlorobenzene with 10 peaks. Right? A lot more transitions are allowed in chlorobenzene than in benzene because of symmetry. And so this tells us the vertical axis, this intensity, and then for the horizontal axis, we have those transition equations. So this is the energy difference equation. Divide that by Planck's constant, and you get the frequencies. And then invert this and multiply by the speed of light, and you get the wavelength. So these are the transition equations. And so now we have everything we need to plot a stick spectrum. Okay, so we have the intensity. We could plot, this I, N to N prime, and then down here we could have the wavelengths of N to N prime. And we pick that particular wavelength, and we have that particular intensity, and we could have a stick. And then we have a different wavelength for a different transition. We have a different stick. And so that's a stick spectrum. And we have enough information now. And this is what Schrodinger plotted in his 1929 paper for the hydrogen atom. That got him the Nobel Prize. So he solved the math, and he said, I have the intensities, I have the wavelengths, I can now see if it looks like hydrogen. And it did. So he did a fantastic job. Okay. I'm not that good. I can do one dimension. So this is the stick spectrum for the energy equation. If we're plotting this versus energy, like I said, if you divide that by Planck's constant, this is proportional to the frequency. So for a particle in a box, this is predicting that our spectra would have equally spaced lines in the frequency spectrum. Now, frequency is equal to C over lambda. And so a lot of times we'll plot things in wave number. So we'll put a little tilde on top, and that's equal to just 1 over lambda, the inverse wavelength. And a lot of times that's in centimeters. So you've seen in infrared spectra, the x-axis is wave numbers, okay? But it's proportional to the energy change in those energy level diagrams, and so it would look just like this. So if we were to plot this particle in a box spectrum in terms of wave numbers, this is what it would look like. We would have equally spaced lines, and we would see our fundamental, you know, and our hot bands. These only exist if the system is hot enough to cause thermal excitation. Because you can never get rid of the ground state, even if you cool it down, you're always going to have the fundamental. Okay? But you may or may not have hot bands depending upon the temperature of the system. So if you cool it down, all of those other peaks will go down to 0, but you'll still have a fundamental. Okay? And in infrared spectroscopy, every one of those peaks that you see is a different fundamental. So you might have a bend, and that's the fundamental for the bend. You might have a stretch, that's the fundamental for the stretch. So you have 3n minus 6 different vibrational transitions, and every one of those peaks is a fundamental. If you really heat it up, you might see a hot band. Okay. But for vibrational motion, the hot bands are going to be at the same frequency as the fundamentals. So you're not going to see them. You have super high resolution, they might be a slightly different, and you could get in there and see, okay, there's the hot bands. But for normal resolution in our labs, you're never going to see hot bands in the infrared. They're going to be right on top of the same frequency as the fundamentals. Okay. And then we have overtones. You will see overtones in infrared. So the overtones, if you notice, this is delta N equals 3 or 5. And so we have those transition equations here. So what does the transition equation tell us? Well, it tells us the energy spacing in the spectrum. So this is the spacing here between these lines. So if I go up from one quantum number to the next, I have these different transitions. They are going to be spaced by this constant out front. And again, this constant is the good stuff. It has the mass. It has the length of the system in it. And so if we match this spectrum, let's say we're doing this, not a simulation, but this is an experimental spectrum. If we can assign those peaks like this and put quantum numbers on every one of those peaks, then we could do a linear regression based upon our quantum number. And this looks a lot like y equals mx. And if you multiply this through, you're going to have the intercept plus b. And so if we do a linear regression based upon n, then we can get this slope, which would be these physical constants. And then we could analyze that slope to figure out what the mass of the system was, what the length of the system was. And this is how we get bond lengths, how we get rotational constants and things, is exactly like this. This is called an assigned spectrum. Whenever you put the quantum transitions on those peaks, you're assigning it. You're assigning quantum states to every one of those peaks. Notice the spacing in the overtones here. This spacing here is larger. So you can see this 3 here. Okay. It's 3 times wider than this blue spacing. And then this overtone here, you can see this 5. It's 5 times bigger than the blue spacing. So we can see all of these different effects in our transition equations. So the transition equations in energy or frequency or wavelength will tell us the spacing in the spectrum. Okay. Here's the same simulated spectrum, but now plotted by wavelength. So what do you notice? Tell me what you see when we go to wavelength.
X-axis is flipped.
The x-axis is flipped, yeah. So all the peaks, all the higher energy peaks, they get crammed down to the 0. And if we were to do like a UV vis spectrum or so on, you might see a peak here, and you see a peak there, and then you would start to see these peaks, and it would just go off scale. And that's what we see in the UV, right? Whenever you put a solvent in there, you have a window for your solvent and your solute, but then eventually it just goes to infinity. Well, eventually what's happening is your solvent is absorbing light. And so you're, as you get to lower and lower wavelength, your samples just become opaque because we have all of these transitions crammed together, and they all absorb. Every photon that's put in there is going to be absorbed by something. And so, but we still have this constant. So if we find the fundamental and we put in 1 for n, for that fundamental, we can still solve for, bond length or mass, etc. So we still have some physical information that we can get from fundamentals. But a lot of times we want to plot versus wavelength when we have really broad peaks because it separates the long wavelength peaks the most. In electronic spectroscopy, we really have broad peaks in these electronic transitions. And so that's why we plot the UV vis spectra by wavelength, is because it stretches out the low energy transitions. The HOMO to LUMO transitions are separated from everything else. And so we can get information that way. But for infrared and so on, we just plot it versus delta E or wave number. I mean, you can do it either way. In the old days, they plotted infrared light in microns by wavelength, but it's really nice to have sort of this equal energy spacing, and so we see that nowadays we plot it versus wave number. And so this is an assigned spectrum versus wavelength, and even in the stick spectrum, I wasn't able to assign all of those hot bands and overtones because they're so close together. I can't even get my, like this right here is 1, 2, 3, 4, 1 to 4. Okay, but these others are so close together that it's even hard to assign them. But I can definitely see that fundamental by itself. So, I think I put in the homework I did last night that you guys can do a stick spectrum now that you have the information for the transition equation for particle in a box and the intensity for the particle in a box. You can now assign and make a stick spectrum and convince yourself that you know how spectroscopy works. Okay. So we've got about 7 minutes. Let's try to quickly do a Kahoot just to cement our understanding. Okay, so there's the game pin. Two more. All right. So this is just the main points from today. Hopefully it's easy for you. We'll see. So absorption and emission have the same probability, meaning they have the same transition moment integral result. Is this true or false? good. Yeah, so this up arrow and the down arrow had the same result. So it's the same integral, so it's the same probability if the populations, are the same. So. Okay, so transition equation is related to which axis of the spectrum? So the transition equation, not the transition dipole moment. Yeah, we use that word transition a lot because that's what we're dealing with. So the transition equation is that difference in energy, difference in frequency, or wavelength. So that's the horizontal axis. So what do you think the next question is going to be about? The transition dipole moment integral affects which axis of the spectrum? So, yeah, so can y'all keep track of the two? Transition dipole moment integral, that's the intensity. Yeah.
Sorry.
And so then, very good. But it's the transition equation, which is just the differences in energy that tells you where the wavelengths are or where the energies are. Okay. So this transition equation tells us about the spacing of, and this is really a vocabulary based on levels versus lines. What do those mean? Okay, very good. The spectral lines are in the spectrum, and it's the spacing of the spectral lines that the transition equation tells us about. That was the slope, the mx plus b. That m is the spacing of those lines. The energy equation, just the straight up energy equation, tells us about the spacing of what? All right, very good. So that E equals h squared n squared over 8ml squared, that's telling you the energies of the individual quantum states. And so that's the energy equation. It tells us about the energy level diagram, and those are energy levels. And you could look at the spacing in those based on quantum number. Okay. All right. And silver, good job. This is too slow. All right, nice. Well done, folks. All right, so that's it for today. Look at that homework and send me your questions. We'll talk later.